So that second tool I wanted to investigate, which is computing area bounded by some polar graph in the xy coordinate plane. Let's talk about how if I have a circle. I said let's talk about. Can I rephrase that? Let's jog our memory from basic trigonometry. That if I've got a circular sector spanned out by a central angle of measure theta, then the area of the circular sector, given that the radius of the circle, say, is a, the area is nothing more than 1/2 times the radius squared times that angle theta if theta is measured in radians. Well, that being the case, if I'm trying to find the region bounded by the graph of some polar equation like this, oops, I said that correctly. If I'm trying to determine the area bounded by the polar graph of an equation like that, in between the two extreme theta values of alpha and beta, I'll partition that amount of rotation into n subintervals of equal length. And I won't draw them all in, but let's concentrate on the ith subinterval, as theta ranges from theta sub I minus 1 to theta sub I. So let's you grab an arbitrary value of theta in there. I'll call it, how about theta sub I asterisk? And we'll use that to come up with a circular sector approximating the area bounded by this equation over that ith subinterval. But because it's a circular sector, its area is computed quite easily by just taking a peek at 1/2 times the radius, which is nothing more than f of theta sub I asterisk squared, times the angle I make spanning out that ith piece. Or how about saying more concisely, 1/2 times r sub I asterisk squared times a change in theta. Now, if I take the limit of every Riemann sum, oh, sorry, that wasn't stated very well. If I take a Riemann sum of this stuff and then take the limits, then the exact area bounded by this polar graph in the xy coordinate plane can be computed as such. My next tool for area. So let's next construct a decent example.